Right, okay, in this video we're going to, in the next couple of videos, we're going to look at refraction in terms of what happens when light travels into materials and then out of them again, and then we're going to look at the features of refractive index and critical angles, etc, etc. We'll focus on that over the next couple of videos. So we'll jump straight into it and observe a refraction happening. So what we're going to do is I'm going to draw, this would be a glass or perspex block. Now you are going to do this experiment as part of the course with me here, so what we'll do is we'll just kind of introduce it and then you'll be able to utilise the theory and the methodology behind it in class. So this is a glass block and we've got a beam of light coming in from air. You might be thinking, why am I writing air? Well, there's a reason behind it and we'll talk about that later. So we've got a beam of light coming in, just like that, and that beam of light strikes this boundary. Now, light, when it passes from a less dense to a more dense medium that it can pass through, as a result of the changing speed of that and changing density of the material, we get this effect called refraction. Now, in order to understand and visualize it, we need something called the normal line. Now, the normal line is basically a line that we utilize to allow us to measure angles to and from. It's a line that is perpendicular to the boundary at which the light is going to be refracted, or reflected, in fact. And we utilize that to suggest what the angle of incidence is in this case. And we'll call that angle θ1 for now. Now obviously we're going to observe something special. As it passes from a less dense to a more dense medium, we would expect the beam of light to bend towards the normal. And as a result, we get the process of refraction. So what we've got here is we've got a situation of beam of light coming in, striking the air glass boundary. It changes direction and bends towards the normal line, and we get an angle called θ2, and we'll call that θ2 just for now. That is an angle of refraction. It's a refraction angle. Obviously the light ray can continue on its route through the glass block. It goes in a straight line till it strikes the glass air boundary on the other side. What would we expect to happen here is that it would then do exactly the opposite of what it did at the previous boundary, because it went from air to glass. Now it's going from glass to air, so we would expect it to bend away from the normal. Interestingly enough, what we can suggest about this angle from the normal line is that it is exactly the same in magnitude as this value up here. So this one and this one are exactly the same, even though my drawing might not indicate that to scale. Interestingly enough as well, that this angle here is the same as θ2. So these two angles are matching and these two angles are matching. And this is effectively just a simple representation of what happens when rays are refracted. So I've already kind of cottoned on to why this happens. It happens because the light ray slows down when it enters into a more dense medium. Okay? Very similar to like a car driving on the road and then driving in the mud. It gets slowed down by the mud. Similar concept. Here we've got the light ray moving through a fairly easy to move through medium, and then we have it going through glass, which is significantly harder because the density is greater. So the velocity is reducing, and from the previous videos we've suggested that v is equal to f lambda. Now what happens as a result of this slowing process is that the wavelengths get bunched up together. That bunching up occurs at this boundary, slowly but surely. Because remember, light isn't a beam, a singular beam, it's a wave. So what we expect to see is what you'll see in your textbooks. I'll attempt to draw it here in a second. It won't be very good though. You'll get a better indication of it in your textbooks. It's very easy to view in your textbooks should you have one. So what we observe here is if you imagine that these are the waves of light coming in, and what happens is that when it strikes that boundary, the wave that's here gets slowed down. Same thing here. And as a result, what we end up seeing is this shrunken wavelength feature like that. I'm actually quite proud of that drawing. That's as best as I can do it for my drawing ability. But like I said, you'll see a video, you'll see pictures of that drawn much better than where I've drawn it there. So the point is that because the velocity drops, the wavelength drops, the frequency of this light stays constant. Okay, that's very important to remember. The frequency of light doesn't change. It stays constant. So the wavelength and the velocity that change as a result of refraction. So, it's all well and good to just talk about this qualitatively and say, oh well, this is what happens, this is what we observe, but we need to quantify this. And we can quantify it in terms of a value called the refractive index. Now, refractive index utilizes the letter N for it. N is equal to C over V. Now, C is another constant. It is the constant of the speed of light, and that's 3 times 10 to the 8. So C is equal to 3 times 10 to the 8 meters per second. That's the fastest speed that anything can travel, that's light. Interestingly enough, what this equation is showing you is it's showing you the proportion of C that is obtained by the light in that object. So for example, in the glass, we can utilize the angles, and eventually we're going to look at Snell's law to help us work out the refractive index, to then allow us to work out the speed at which it would move in that material. So as I've already mentioned, Snell's law is going to enter in very strongly here, because Snell's law is what we'd utilize to allow us to work out this value of N right here. And I'm just going to rub out the words over here because so I can have some space to write them. So Snell's law then. Snell's law is termed as N, it's proper nomenclature, so N1 sine theta 1 is equal to N2 sine theta 2. Now what's important about this equation is that all of these values can be found from the drawing I've drawn on the board here. And what we have is a situation where N1 is the material that it comes out of. The material, proper N, that might be helpful. N1 is the material it comes through before striking the boundary. In this case, it's air. That means that N2 is the material that it passes into. So that is the glass in this case. Theta 1 and theta 2, well, theta 1 and theta 2 I've already coined on the diagram. Theta 1 is the angle of incidence at which the ray of light strikes the boundary from the normal line. Theta 2 is the angle of refraction, is the angle at which from the normal line the ray is reflected upon passing through that boundary between the two densities of material. And we can utilize this, and we will do in a video or two's time, to allow us to work out the refractive index of a block. You will do this practically as well by measuring multiple angles. Okay, so in the next video we're going to look at critical angles and whatnot, before we then, in the video after that, we'll look at some examples of how we can utilize this mathematically and do some calculations on it.